Good morning and good evening. Well, thank you, Rob, for that excellent beginning and introduction on gold grains. I'll just share my screen here. There we go. So the next part of this presentation will be...
Sorry, Britt, to interrupt. We're just seeing the back end of the PowerPoint.
Oh, thank you. Let's share this one. Okay.
There we go. Perfect.
Awesome. Thanks, Vanna. So thank you to Rob very much for that. And the next part of the presentation is dedicated to creation of this geochemical template or workflow, or to try and answer the question, what do I do if I have gold grains, but I'm not Rob Chapman and I don't have a lifetime of experience looking at microchemical mineral inclusion data? So that's what we'll go through today. The first pieces that I did in this workflow were some very routine data pre-processing steps, like cleaning, removing zeros and negatives and less than, replacing them with positive half detection limits, and then some balancing of the data. So when you're doing any kind of machine learning techniques, we won't talk about it too much, but when you're doing any machine learning techniques, it's very important to have balanced data sets, which means that each group or each category that you're working with has approximately equal number of observations. You'll recall from Rob's second to last slide that he had a pie chart showing the majority of the data came from orogenic deposits, and then a smaller subset of data came from skarns or low sulfidation epithermal systems or alkalic porphyries. So in terms of balancing, we did something called synthetic minority oversampling technique, which basically means we created synthetic data for the classes that were more poorly represented. In this case, the example here on the right-hand side is low sulfidation epithermal. And once the class balancing was finished, we did a linear discriminant function analysis. So this is a classified technique, which requires a priori knowledge, which is a way of saying that we took the information that we have, in this case, some training data, and we said, we know these gold grains are from those deposit styles. So which subset of the elements that I happen to have in my database are going to do the best job at, in some linear combination or some equation, which of these elements is going to best separate my different deposit styles? And it turns out that these elements listed on the bottom were the best. So moving forward with those, we wanted to create a machine learning classification algorithm. And of course, don't worry too much about any of this, because this is basically just to show you under the hood so that you can see the guts of this user manual that we will be creating. And you can see that it's not witchcraft at all. But you don't need to worry about recreating this. This is just some detail for you for your confidence in the method. So when we created this machine learning classification algorithm, we trained and tested several different algorithms like k-nearest neighbors, support vector machines, random forests, neural networks, and phase. And it turned out that the random forest had a classification accuracy of 0.84, which is quite good. So on the right-hand side here, you'll see this receiver operating characteristic curve, set of curves, which is also called an area under curve or an area under receiver operating characteristic curve. Love the acronyms here. And you can see that the random forest, which is in green, climbs the y-axis most quickly. So for an algorithm to be the most effective or the most productive, you want it to climb the y-axis quite steeply and then level off. What you don't want is for it to follow this y equals x line, because that is the same as having a series of random results. So to evaluate the model's performance, you want it to have a very good true positive rate and a very low false positive rate. The other thing, though, that you don't want is for it to basically shoot up to the value of y equals 1 and then shoot across in a pattern like this, because that means that your model has been overfit. We don't want that either. In any case, we'll move forward from there. And at the end, we get to visualize our results. So on the right-hand side here, we have a tree diagram, and the tree diagram, several of those put together make up the random forest. So for example, a random forest is a combination of tree predictors such that every tree depends on the values of a random vector sampled independently with the same distribution for all trees in the forest. So we see when we have a specific value of gold, higher than that would be classified as orogenic, lower than that would be classified as epithermal. And then the next variable to be assessed is copper. So a specific value of copper would tell you that you have a low sulfidation epithermal system or an alkalic porphyry system, and the same with mercury. And then finally, we can visualize all of that into these Pythagorean tree diagrams as well, which are kind of fun looking. On the bottom, we see the orogenic arm, and then we see the low sulfidation epithermal arm, and then finally the alkalic porphyry arm. And so at the end of this is to say, don't worry too much about recreating this workflow, because what we'll do is take all of this and package it into a user manual, which is to say that we'll take the subject matter expert of the incredibly talented Rob Chapman and his vast experience with gold grains, microchemical data, and mineral inclusions. We'll package that up together with this machine learning workflow that you guys are all very comfortable with now. And then you can do your own analysis moving forward on your own gold grain chemistry. So what we'll do to finish up the project is we'll complete the laser ablation ICP-MS analyses. We'll wrap up some of the SMN analysis with some sample suites from UBC, including some SCARNs, which will also help to flesh out the data set in terms of different classes. We'll refine the compositional templates and publish the database. Then we'll produce the user manual that I was speaking about a moment ago, and the project will be completed by Roundup 2022. So thank you very much for your attention this morning, and we would love to have any questions.